Part 6, Coding. After defining and initializing all variables, we define a new function to calculate the volume of the pyramid. This function has a return value of type S32 and is called Calculate Volume Pyramid. It needs several input parameters, namely the pointer for the result, the height and the width. All of these parameters are passed as S32 variables with the associated const S8 shift factors, as described in the concepts in Part 1. Our function, which calculates the volume of the pyramid, contains the arguments S32 volume, const S8 volume shift factor both as pointers, S32 height, const S8 height, shift factor, S32 width, const S8 width, shift factor. We create two new intermediate variables for the calculation, namely a variable for the base area of the pyramid and a variable res for the result. The variable for the base area receives the shift factor 20, as the base area can be a maximum of 1532.7225 square meters due to the prerequisites of the application. The base area is calculated by squaring the width. For this we can use the EC-LIB macro EC-LIB square. Moreover, remembering our school days, the volume of a pyramid is calculated using the formula, volume equal a third of base area multiplied by height. After squaring the width, we divide the base area by 3. This order of the calculation is selected to avoid an overflow in the subsequent multiplication. If we were to first do the multiplication area by height and then divide by 3, the risk of overflow would be greater. However, we must be aware that by dividing the area by 3, we lose accuracy. Finally, we call the macro EC-LIB mul to multiply the 1/3 base area by the height. When creating the function calculate volume cuboid, we perform the same tasks. We create a function with the appropriate input and output parameters, then define intermediate variables again and finally describe the calculation for the base area of the cuboid and the final multiplication base area by height. We receive two functions that calculate the volume of each geometric body. Afterwards, we return to main and call both functions there. The results are written in volume pyramid and volume cuboid. Since we want to know which of the two bodies has the larger volume, we compare the result of the two functions. For this comparison we use the EC-LIB is less or equal macro. In order to use this macro, we need a new intermediate variable of type EC-LIB bool into which the result of the comparison is written. This variable is defined and initialized at the beginning of the main function in the definitions and initializations section and is called res comparison. We initialize res comparison with EC false, since we want to compare if the pyramid is smaller in volume than the cuboid. Due to the much larger maximum value of the pyramid's volume, it will rarely occur that the pyramid is smaller than the cuboid. Therefore, it makes sense to set res comparison to false. We now fill the macro EC-LIB is less or equal. The variable res comparison represents the output value and the two variables volume pyramid and volume cuboid provide the input for comparison. With this the EC-LIB will now calculate if the pyramid has a smaller volume than that of the cuboid. Finally, we design our application to be a little more user-friendly by setting two outputs via printf. We use an if query to decide which output the user should receive. Either the pyramid is less than or equal to cuboid in volume, or the pyramid is larger in volume than the cuboid. Finally, we build our project again. Our application for volume comparison of pyramid and cuboid is ready for use now. Further information on EC-LIB can be found on EC-LIB.com. If you would like to get to know EclipseSigner and find out more about training opportunities, visit us at EclipseSigner.com.